All right, so we're going to finish up 15.5b. We were talking about mass and center of mass and the moments, and what we were talking about in 15.5a was if we had a constant density. Well, now in 15.5b, we've been talking about a variable density, and these are the formulas here that we're going to need if we have a variable density. So remember that your moment is the sum of all of your x sub i's, m sub i's. The moment with respect to y is going to be a double integral of x rho x of y dA, and the moment with respect to x is going to be the double integral y rho xy dA, and then the mass is just the double integral of the rho xy. So your x bar and y bar are up here in the right hand corner. Whoops, didn't mean to do that. All right, so let's kind of remind ourselves real quick. I don't want to spend too long on this video because these problems can get very lengthy. The general idea was that if I have some kind of a lamina of some kind, we'll call it, at least that's what they like to call it. And here is your lamina. On this sheet, or whatever it is, on this surface, you've got some kind of variable density. The density is not consistent throughout the whole thing. If it was, and this was a square, it'd be very easy to see that the center of mass would be right in the middle of the square. But in our case, maybe the center of mass is not in the middle of the square because the density is more weighted towards the upper right-hand corner, and maybe your center of mass is, right here. And again, what that means is you're going to have equal mass on either side of this thing vertically, which means it's going to keep it from rotating around that vertical axis if I put the center of mass right there, and then it's also going to have a center of mass horizontally. Again, that right there, that would be your actual center of mass, and the horizontal one would keep it from rotating around a horizontal axis. Basically, you want to keep this thing completely steady. You want to keep it balanced. So what you would have is equal mass on either side vertically and horizontally. Horizontally. And that's the general idea. So if you put like a fulcrum or some kind of a very thin something underneath of that thing and put it right in that spot, it would balance completely. All right, that's just a quick reminder of what it is. Now, let's look at an example problem. We've already done one, which had to do with the charge. It's the same general idea. We want to find the mass and center of mass of a triangular lamina with the vertices given as 0, 0, 1, 0, and 0, 2 if the density of the function is given by rho of xy equals 1 plus 3x plus y. This problem is a long problem, so I may or may not do the entire thing, but I'm going to at least work down a little bit with you so that you guys can see some of the algebraic simplifications you're going to want to do here. You can do this in other ways, and you can do full expansions, and it might be just as easy for you to do it that way. It depends. To me, it takes a little bit longer, so I try and find whatever little things I can to make the problems a little bit quicker. All right, so in general, our mass was the double integral of our density function, 1 plus 3x plus y, over this region. Well, fortunately, they've given us just about everything we need. They gave us the line y equals 2 minus x. They gave us the coordinates of everything. They actually gave us the center of mass, so we know what the answers are supposed to be. If you look right there at your drawing, 3/8, 11/16. So you can match those answers if we don't finish the problem. All right, so we're going to go ahead and do this as a type 1. So that means y is going to vary from something to another function of y. X is going to vary from number to number. So x is going to go from 0 to 1. Y is going to go from 0 at the bottom here all the way up to 2 minus 2x. Here, that is supposed to be a 2x up there. It just doesn't look like it. All right, a little better. And so y is on the inside. X is the last piece because it goes from 0 to 1. So let's go ahead and find the mass. So we're going to have integral from 0 to 1. Integrating with respect to y first. We get y plus 3xy plus 1/2 y squared from 0 to 2 minus 2x dx. So let's go ahead and plug in 2 minus 2x for the y's. 2 minus 2x plus 3x, 2 minus 2x plus 1/2 2 minus 2x squared dx. So what you should see is that there is a 2 minus 2x in every problem. I'm going to factor out a 2 minus 2x. Can't pull it out to the front of the integral because it still has a variable in it. So it's 2 minus 2x. Oops. And what that leaves us with is, out of this term, that leaves us with 1. Out of this term, it leaves us with 3x. And out of this term, I'm pulling a 2 minus 2x out, so I'm going to have a 1/2 2 minus 2x left. So 1/2 of 2 minus 2x is going to simplify to 1 minus x dx. Now, why did I want to do it that way? Well, if you look carefully, what we've got here, this inside of this thing, let's see, as 1 plus 1 is 2. 3x minus x is plus 2x. These two things are conjugates. So when I FOIL this out, it becomes very simple. It's first times first and last times last because the outer and inner will go away. So I've got the integral from 0 to 1 of 4 minus 4x squared. Now, you could have, going all the way back up to here, you could have multiplied and distributed all this out right here. You could have FOILed all that and distributed and then combined all your like terms. Eventually, you get to this, but I think it was easier to do the factoring up front and then simplify. All right, so now we're going to go ahead and take antiderivatives. So we get 4x minus 4/3 x to the third from 0 to 1. Plugging in a 1, we get 4 minus 4/3. Plugging in 0, you get nothing. 4 minus 4/3 is, what is that, 12/3 minus 4/3? 8/3. So there's your mass. All right, and the reason that it's important for us to find the mass, because according to the previous page, I need the mass to find the moment, right here and right here. I need those, so I'm going to divide each one of the moments by the mass. But dividing by the mass, because it's a fraction, is really multiplying by its reciprocal. So x bar, in this case, let's start this way over here to the left, is the moment of y divided by the mass. But the mass is 8/3, so instead of dividing by 8/3, I'm going to multiply the moment of y by 3/8. Then the moment is the same integral, or at least the same bounds, I should say. The only difference is now I have to multiply by x. I have to multiply my my density by x. So our original density here was 1 plus 3x plus y. And then it's still going to be, in this case, we're going to go dy dx. Haven't changed. I don't see any reason why you would want to change which way you're going to go. So let's see. Distributing the x through, oops, distributing the x through, we're going to get x plus 3x squared plus xy dy dx. Now we can take an antiderivative with respect to y. So we're going to get xy plus 3x squared y plus 1/2 xy squared, evaluated from 0 to 2 minus 2x dx. So again, let's go ahead and plug in the 2 minus 2x for the y's. So we have x 2 minus 2x plus 3x squared 2 minus 2x plus 1/2 x 2 minus 2x squared dx. So again, what you should see is that I have a 2 minus 2x in common, but I also have an x in common in all of these. So when I factor this, I'm going to factor out an x and a 2 minus 2x. And then that's going to leave us with, out of the first term, it leaves us with 1. Out of the 3x squared 2 minus 2x, it just leaves us with 3x. Out of the 1/2 x 2 minus 2x squared, we're going to take one of the 2 minus 2x's out and the x, so it's going to leave us with a half of 2 minus 2x, which again is 1 minus x. This should all start looking familiar. What you should notice is all of this is exactly the same as what we did up in the top, up in the mass portion. The only difference is I have that extra x. So all of the thing I just highlighted in blue is going to simplify to our 4 minus 4x squared. It's exactly the same. So I've got 3/8 integral from 0 to 1 of x times 4 minus 4x squared dx. I cannot guarantee that this will work for everything, but I'm thinking that it might. So you might want to check that as you're going through some of these problems and see if this is the kind of thing that happens. So this is going to be 3/8 integral from 0 to 1 of 4x minus 4x cubed dx. Integrating, we get, that's the antiderivative of 4x is 2x squared. Antiderivative of minus 4x cubed is minus x to the 4th from 0 to 1. Plugging in a 1 on the inside there, I'm going to get 2 minus 1, which is 1. Plugging in 0, I get nothing. So really, we're going to get 3/8. Interesting that the mass is the same thing as the x-coordinate of the center of mass. Don't know if it's coincidence or not, but it seems like it might be. All right, I am likely not going to work out y bar just because this is starting to, excuse me, approach 15 minutes already. I want to keep this under 20 if I can, but we'll set it up. So y bar is mx over m. Once again, dividing by the mass is going to be multiplying by 3/8 out front. Integral's the same. Excuse me, the bounds are the same. Still do it as a type 1. The only difference is now it's y. 1 plus 3x plus y. And what I will tell you is that this one does not work out with a nice little trick towards the end. This one's just, it's long and algebraically messy. So just warning you there. As a matter of fact, we're not going to go through the entire thing, but you do know the answer is supposed to be 11/16. So once you go ahead and simplify that, and again, it does get algebraically messy. It gets down to a point where if you kind of try and do some factoring, pulling some constants and stuff out to the front, you get down to a 2 minus 2x quantity squared, and then times a 5x plus 7 or something similar to that. So it's not horrible, but it's a bunch of, you have to do some foiling at the end. There's just no choice, unless you can find another shortcut that I didn't see. All right, number 3. So it says a lamina occupies the part of the disk x squared plus y squared is less than or equal to 1 in the first quadrant. So we are just basically talking about that. Find the center of mass if the density at any point is proportional to its distance from the, that should not say the x-axis, that should say the y-axis. So correct that. All right, so let's see. Find the center of mass. Well, we know we're going to need mass. If the density at any point is proportional to its distance from the y-axis. Well, the distance from the y-axis at any point in time is just going to be an x value. So no matter how far out from the y-axis we go, whatever that is, that's an x value. So that's the distance from the y-axis. And the fact that it says proportional means we need to introduce a proportionality constant. So our rho of xy is simply going to be some constant of proportionality times x, proportional to the distance from the y-axis. The distance from the y-axis is x. So this is a portion of a circle. So we could certainly use y equals the positive square root of 1 minus x squared. It seems to me, however, this would be much, much easier to do in polar because it's a portion of a circle. So our mass in polar, okay, it still doesn't change as far as a double integral is concerned. Got to take a double integral. But remember that whatever we're going to put on the inside here is our density function. It's going to end with an r dr d theta. Don't forget that extra r. It's part of the conversion factor into polar. So our density function is going to be k times x, but in polar, x is r cosine theta. So x in polar is r cosine theta. So this is going to be k r cosine theta. Now we just need the bounds. Well, r, pretty obviously, is going to go from 0 out to 1. And theta ranges from 0 up to a 90-degree angle, which is pi halves. So there's our equation for our mass. And the really wonderful thing about this is we can use Fubini's theorem here. This is completely separable as far as the variables are concerned. So k is a constant. It can be pulled out to the front. The next one is 0 to pi halves, so that's our theta. And our theta parts are cosine theta d theta. And then it is a multiplication. And then we've got integral from 0 to 1 for our r, which is r squared dr. So this mass is going to be pretty easy to calculate. K times the integral of cosine, which is sine theta, from 0 to pi halves, times the integral of r squared, which is 1/3 r cubed, from 0 to 1. So let's see, we are going to get, okay, so sine of pi halves is 1, sine of 0 is 0, so that's times 1, times the integral of 1/3 r, so that's going to be 1 minus 0. So ultimately, what we get, I'm sorry, not 0, it's 1/3, sorry, is k times 1 times 1/3, so our mass is k thirds, k over 3. All right, our x bar is going to be our my over m, which again, remember, introduces an extra x. So it's going to be dividing by the mass. Dividing by k thirds is multiplying by 3 over k. Integral goes from 0 to pi halves. Integral goes from 0 to 1. Okay, so we have k. Our original density function was r cosine. And we have to multiply that by another x value, which is again r cosine, r dr d theta. So this was our original density. This is our x, and then here is your dA. Let's make that look like an x and not an alpha. There. So we'll finish this one, and then I'll give you the answer for the y bar again. So let's see. This k cancels out that k, which is nice. That leaves me with a constant of 3 out front. Once again, I can separate the variables here. I've got 0 to pi halves of the theta part, which is cosine squared theta d theta. And then the r part is r. I got 3 r's, so it's going to be the integral from 0 to 1 of r cubed dr. So, in order to do the cosine squared, I have to use a reduction formula. So it's 3 integral 0 to pi halves, 1 half 1 plus cosine 2 theta d theta. And then the r cubed part, that's just 1/4 r to the 4th from 0 to 1. So let's see, I've got a bunch of constants here. I can pull all the way out to the front. I've got a 3, a 1/2, and a 1/4. Multiplying all that together gives me a 3/8. The antiderivative of the 1 plus cosine 2 theta is going to be theta plus 1/2 sine 2 theta, evaluated from 0 to pi halves. And then I've already taken care of, oh, no, and then I've got to do the, I've already pulled the 1/4 out, so plugging in 1 and plugging in 0 just gives me times 1. So really, whatever I get from this 0 to pi halves integral. So plugging in pi halves first gives me pi halves plus 1/2 the sine of pi, but that's 0. And then plugging in 0 for both theta and there is going to give me 0. So 3/8 times pi halves. 3 pi over 16. That is the center of mass for x bar. Now we need y bar, which again I'm not going to work out completely, but I'll help set up with you. So the only difference there, still 3 over k, integral 0 to pi halves, integral 0 to 1. Still have our k, r cosine theta, but now remember we have to introduce a y here. So y is r sine theta, and then r dr d theta. So again, here is rho, here is y, and this is your dA. So once again, you can separate these things, which is nice, and you're going to have one with theta where you've got cosine theta, sine theta. A very simple u substitution should get rid of that. And what you should end up with here is 3/8. So your x bar, y bar, in this case, is going to be 3 pi over 16, 3/8. All right, one more page. And I am sorry, this is not going to be under 20 minutes. It's going to be about 25 minutes. Why this thing says example 4 down here at the bottom, I have no idea. That should not be there. As a matter of fact, for this part, it's just going to be giving you some formulas because really there's not a lot we're going to do with this. You may deal with more of this stuff in physics, but you can have basically 3 types of second moments. Thinking about kind of like almost like it's not a second derivative, but a second way to measure this. They're called the moments of inertia. Again, this is more of a physics topic. You can have a moment of inertia about the x-axis, about the y-axis, and about the origin, which is also known, as the polar moment. And if you kind of think about that, Typically, a moment is how to keep something balanced around the horizontal, around the vertical. This is how to keep something balanced around the origin, so spinning it almost. Um, so you have to keep it balanced in a polar sense. I'm really just going to give you these formulas. You probably need to use one, but just plug in the formula. It's really not that difficult. If you want to find the moment of inertia around the x-axis, typically it's an I sub y, which is a double integral of x squared rho of xy dA. If you want to do it around the y-axis, you can probably guess we call this I sub x, and it'll be a double integral. I should put over d, over your domain. And this one is y squared rho of xy dA. And if you want to do it around the origin, the moment of inertia about the origin, it's still a double integral over d. This one is x squared plus y squared rho of xy dA. Now you could certainly attempt to do this in rectangular, but hopefully you'll notice that x squared plus y squared is r squared. So you are much better off doing this in polar if you have to do moment of inertia around the origin. Okay, that's all I got for you guys. Hopefully that helps. Enjoy.